Hello and welcome to Random Forests Explained for Beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video I'm going to talk about random forests. Its ingredients include bagging, decision tree, feature bagging, sometimes called random projection, and then we will discuss the general strategies for random forests, and finally we will wrap up our video with the Python code implementing random forests in scikit-learn. If you are new to our channel, just about AI sciences, we deliver here a lot of data science consultancies and courses. Please go through the links below and you will find out the world of data science in much easier, explained in much easier way with codes and with documentation, with books, and a lot of other helping material in that regard. So let's begin. First of all, let's talk about bagging. By the way, we already have a YouTube video on bagging, what bagging is, and there, if you see the link in this video, link below in the description, you will find out the link of bagging, and we have explained bagging at depth in a separate video. So for details, please go to that video. However, in this video, to make this video roughly independent, I will just go through briefly what bagging is. So what happens in bagging is that if you for example see on the right hand side the data set, here we have example 1. We have 6 features: x1, x2, x3, x4, x5, x6. These are 6 features of some data, some object, and these are the feature values. So example 1 has feature value 1, x2 feature value is 1.01, then we have minus 4.99, 4.99, then we have 1.2, and these are the feature values. And the final column is actually the class label. So this is a classification data, a toy data set, just to explain the example. And here we have 24 data points, or 24 samples along with their class labels. In bagging, what we really do is we pick a random sample of training examples. For example, from our training data, we maybe randomly pick example number 1, which means the whole row of example 1, maybe example number 7, example number 12, maybe 13. This selection is completely random. So once we go to this random selection, for example, in this particular case, we have a selection of example 1, example 7, example 12, 13, 17, and 20. In the most general form, this selection is no longer a set. This selection indeed is a bag, which means an example can be selected again and put inside the collection. That's fine. And that's the reason why it is called bagging. Anyways, so that's one kind of, you can think of this as a bag. And obviously when these rows are selected, for example, row 1 is selected, whole row is selected along with its target label. Then row 7 is selected all the way up to its target label. All these data sets are sampled, all these data points are sampled, and a decision tree is trained on this sample. In the next slide, I will explain what a decision tree, although we have a full-fledged video on decision tree, a separate video on decision tree as well. This is the first bag, or first, you can say, a sample of the data. Then we can pick another sample of the data. For example, a random sample, for example, 3, 5, 8, and maybe this 12 is selected again, 15, and let's say 19 and 23. So that's a second sample of the data, which includes 3, 5, 8, 12, 15, 19, and 23. And we train a decision tree on this as well. So we make a lot of different random samples, or bags. You can think about bags of this data, and we train independent classifiers. In this particular case, we are using a decision tree classifier. However, in general, one can use any classifier. In the case of classification and in the case of regression, one can use any regression tree, or any regression algorithm. So finally, what happens is all these decision trees, they are trained on different subsamples of the data. And when a test point appears, the test point actually is classified through the first decision tree if that's a classification problem. The same point is classified by the second decision tree and so on. And in the case of classification, the mode of the decision or the majority vote wins. So xt is assigned a class which is reported by most of the classifiers. And in the case of regression, xt gets a target which is the average of all the regressors in this whole bagging scheme. So in bagging, what we do is we do subsamples of the data, and on each subsample we train a classifier, typically a decision tree, and there are a lot of decision trees that are trained independently on different random samples. And these samples in theory should be, you can take it with replacement or without replacement. Different implementations exist. In the pure form, these samples are taken to be with replacement. And different decision trees, they are trained, and in the case of classification, a majority vote is used as a final label, and in the case of regression, the averaging of all the decisions are assumed to be the final target. It turns out that the bagging basically has low variance, and it performs better as compared to a single decision tree or a single classifier in general, and has less chances of overfitting. But one assumption for bagging is that all the learners, like this decision tree is a learner, this decision tree is another learner, and so on. All the learners, they should be statistically independent. So that's the assumption. Basically, if this assumption is followed, bagging works surprisingly very well. One problem with decision tree classifier, if we use, because in literature, mostly bagging is used with different classifiers, but decision tree is reported the most. Then most of the people, they pick decision tree as a base learner, and they build bagging on top of bagging with respect to that. The way the decision tree works is as follows. For example, if this is the data that is given to you, by the way, please follow the link in the description to understand decision tree in detail. Here we already have a video on decision tree on our channel, but here I explain briefly that the decision tree works in picking the most suitable, for example, feature, and that feature has maximum splitting power, where splitting is defined by a particular criteria. And that's how the decision tree works, by building the sequential kind of decisions. Now the problem with decision tree, using a decision tree as a base learner inside bagging, is that if you have several decision trees and you give different subsamples of data to all decision trees, different subsamples, they will rank or they will order the same kind of attribute, if that's an important attribute, in the same way at the top, and the ordering of this attribute makes different decision trees, even though they are trained on different subsets, different decision trees, they will become correlated, and they will not stay statistically independent, which is the assumption for working better in terms of bagging. And that's basically, if we combine, if we take the idea of bagging, and if we take the base learner as decision tree, and somehow we can break this dependence and correlation caused by the decision tree, that is basically the main idea of random forest. And what is done in random forest is, again, we have some subsamples of data. Let's say we pick a bag of data. Let's say this is one subsample. Now, rather than picking all the features, we pick some subsamples of features as well, sometimes known as feature bagging, or also known as random projection. random projection. So the first bag may use feature x1, x3, and maybe x4 along with the data. So the data set will consist only on feature x1, x3, and x4, and these features are randomly selected. And the second bag may be another bag. For example, the bag here I am highlighting with the red color. Maybe the 10 is picked again, 13 and 17. This bag may use a different subset, maybe x2, maybe x4 again, and x5. And yet another subset, or for example, subset of data may use a different subset of features. In that case, for different subsets of data as well as the features, if you, for example, use different subsets of features randomly selected, then the expectation that the different decision trees they will be correlated becomes lower, and the assumption that different base learners they should be statistically independent for bagging to work very well is imposed better as compared to picking up all the features in the case of when the base learner is really a decision tree. So and that's the idea of random forest. So pick a random subset of data, random samples, maybe sample number 2, 4, 7, 11, 14, and 16, completely at random. Then out of the features, pick a random subset of features and build a decision tree on top of that. So let's say that is decision tree 1, train a decision tree. Now pick another subset of subset of data, and randomly select the subset of features and build another decision tree, let's say decision tree 2, and build, for example, k decision trees. Obviously, all these decision trees, they're built on random samples. They may be probably different, and the random samples both in terms of data as well as in features. Now if a new test point comes in, its features that are required by the selection for decision tree 1 are selected and it is classified. Then the subset of features that is required by decision tree 2, that subset is picked and it is classified by decision tree 2, and similarly for decision tree k. And then in case of classification, a majority vote works, or in case of a regression, an averaging works. And it turns out the random forest using these decision trees is actually very, very powerful and very, very fast classifier and regressor as well. More benefits are using all these kind of techniques in parallel. For example, what if we want to train all these different decision trees in parallel on GPUs or on distributed environment? So if you have a lot of data with a lot of features, you pick a subsample of the data, you pick a sample of the data, you subsample the features, and that's your smaller data set with smaller number of features. Train it on an independent machine or some GPU or something like that, and do the same stuff for different subsamples of data as well as features. So you can apply all these computation in parallel, and the training will become very, very fast because all different base learners, they are working completely independently. They have no correlation at all, at least theoretically. And that's very, very powerful and makes it very convenient and very practical to use in practical purposes in most of the applications. I should also mention one point that although the idea of random forest is to, given the data, let's say these are different rows of the data, and let's say I pick this feature, I pick this feature at random, and then this feature at random, and I let's say pick, for example, there are several rows. I've picked just these ones that are there with these reds. Let's say pick these 3 rows, and out of these 3 rows I pick, or I pick the 4 rows, and I pick the 3 features. Let's say there are several features and there are several data, the size of the data set is large. and I come up with a smaller subset of data, maybe a classification data, or maybe let me call it at x1 and y1. Then I may go through the data set again and I pick another sample and I come up with another data set. So that is my data set 1 with smaller number of features and smaller number of data points. That is data set 2, and maybe I come up with k different data sets. Now, in classical approaches in random forest, in all these data sets, one should train a decision tree. But in general, this is no longer a restriction. One can come up with using any classifier or regressor on different data sets. For example, in general, one can use SVMs, for example, or logistic regressions, or even neural networks. Or maybe hybrid. I mean, the first data set use SVM, the second data set use logistic regression, the third data set use some other classifier, and so on. So the general approach to random forest is no longer just training a decision tree on all different subsets of the data and the subsampling of features. In fact, you can use different kind of models inside. But in practice, decision tree actually is bound so tightly to the random forest that whenever the random forest idea comes in mind, it's the decision tree that mostly people are referring to. So enough talk, I guess. Let's go to the Python and see some live coding. Why not? So let's import some libraries from scikit-learn.ensemble. I have imported random forest classifier and I have renamed just aliases RFC. I've imported the train test split from scikit-learn, confusion matrix from scikit-learn again. This is SNS for displaying the confusion matrix a little better, NumPy for data. And if any plotting is required, PLT, SNS.set, that's the environment for plotting. Better plotting, you can say. Okay, so now after loading all the packages, let's load the data, and we are working just on data, which is the iris data. So the data set has 4 attributes and 3 classes. Although in our video I have explained binary classification, but it works on any number of classes no matter what, because it's it is just the ensemble. It is, I mean, whatever the limitations are there, whatever the beauties are there of the base learner, that is reflected in the ensemble as well. So random forest is an ensemble. So if, for example, your base learner just works on binary classification, then the random forest will be better on binary classification. If your base learner works very well on multi-class classification problem or regression problem, then your random forest will be having that property and so on. So random forest, just think about that as an ensemble. Okay, so the targets, why? The different targets here are 3 targets: Setosa, Versicolor, and Virginica. So let's just get the data out, 4 features, and let's say we have make a train test split. We hold the 20% of the data as test data and 80% of the data as our training data. So let's do that. So here is our random forest classifier call. This n estimator basically is the number of splits or the number of subsampling of the data, or the number of decision trees for that matter. How many decision trees you're going to build. And that's a parameter, and I mean, best way to select this parameter is to go through using cross-validation. And then I will call the function fit to fit that model on our training data. Then we'll make the prediction using the predict function. And then let's see the performance of this classifier on our test data. So that's a confusion matrix, and it is displaying this is the true label, and that is the label selected, that is the label predicted by our random classifier, a random forest classifier. And remember, this is on the test data, which is not used at the training time. So you can see all the 10 Virginicas, they are actually they are all the 8 Setosas, they stay Setosas. So the true color is Setosa, and the predicted color, the predicted type is also Setosa. Versicolor, the true label is versicolor for 11 samples, and the prediction is also versicolor. Great. For Virginica, the true label is Virginica for 10 examples, but the true class was Virginica for one sample, which is misclassified as versicular. So pretty good performance, although this was a very small data set, but just I've just explained this just for checking how to implement random forest classifier in scikit-learn. By the way, there is a random forest regressor as well if you want to apply this on a regression task. So that's about it. I guess you have enjoyed our video. By the way, for bagging, for decision tree, there are full-fledged videos already available on our YouTube channel. If you want to understand those concepts in more detail, please go through the links in the description. And if you have liked our video, please subscribe our channel, press the like button, and share this video among your friends. And yeah, hope to see you next time.